I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. I just ask you to bless this class. Help us to just settle the remaining topic before the test and just help the students to draw together their thinking as they prepare for the upcoming first test next Tuesday, Lord. In your name I pray. Amen. Okay, so yeah, one of you had a question about the notes. I had a step where I took the derivative of, I guess this was the unit tangent in some example, and I was just telling you that when we take a derivative like this, I mean, you either can multiply the scale factor up front into both components and do like quotient rule on both ones, or you could do the product rule like I did here. I mean, you got options, but so after, I don't know if you had a chance yet to finish it, but yeah. Okay, anyway, so let me erase that because that's not what we're actually talking about today. So I asked you guys to watch an example yesterday, and I think in that example I assumed that you knew how to do something, which in particular is take the integral with respect to arc length of a scalar function. So I'd kind of like to go back to basics and just define that for you and talk a little bit about, at least geometrically, how you might understand it. Well, in 2 dimensions I can give a specific meaning to it. So let's just say understanding the integral over a curve of f ds, aka the integral with respect to arc length. So this is a new, perhaps new concept of integration for you, depending on how your Calc 2 instructor did things. So let me just try to explain to you. Here's one geometric interpretation. So if it's a 2-dimensional curve, it's a curve in the plane, right? It's a curve in the plane, right? And let's suppose that the curve looks like, I don't know, like that. So here's my curve, all right? Then I could graph the function here, f. F is something like, it's a function from, say, R2 to the reals again, right? The curve is some subset of R2, so it's a curve in the plane, current discussion. And I could graph the values of the function over the curve, kind of like a curvy tent. Right, so the height of that tent would be governed by the value of f. So it would look something like, like the value of the function is positive, then maybe it's decreasing, maybe it shrinks to 0 here, right? Then maybe it goes up again, and then maybe it shrinks back down, I don't know, 0, and then maybe it gets positive again, shrinks back down. Maybe it even goes negative down here, right? And then you could sort of connect that. So I don't know if you can quite make sense of my picture or not, but this would be some sort of, I should probably have been less ambitious with my curve. Let me try something else. A little bit less ambitious. The curve might look like this, right? The values of the function over the curve might be something like this, like this, like this, like this, like this again. Right? So the question is, what's the area of this blue curtain over the black curve? Right? What would the area? If I keep the function positive, it would just be straight up an area. In principle, if the values of the function happen to be negative, then you could count area of the curtain below the xy plane as negative, just like we do with the regular integral, right? And so how would you calculate the area of such a curve, such a tent? Well, what you could think about is just kind of like just laying it flat, right? And you could chop it up into little pieces, right? So if you chop this up into, let's just pick on a particular little bit, and I'll try to draw it in some other color. Something like, say, this, right? This piece right here, well, this length would be what we call ds, the arc length, right? And what would the height be? Basically just f of the point, right? So the little bit of area from that little, little sliver, if you will, little infinitesimal piece of this tent, the little dA there, would be the value of the function at that point, right, times ds. Now the way to actually calculate that would be something like this. dA is equal to f of r of t times what? Well, times ds dt. That's how we'd actually calculate that. With a parameterization, we can convert ds to speed times dt and then do an appropriate integration over the range of t. That's in question. So that leads us to definition. The integral over the curve of f ds is equal to the integral, let's say from a to b of f of r of t times the magnitude of dr dt dt, where c is parameterized by r, which goes from AB to the curve C. Now, my picture about the curvy tent, it doesn't make sense really anymore when you think about it being a three-dimensional curve, right? If it's a curve in 3 dimensions, where do you draw the tent? I'm not sure, But this integral would still have meaning in higher dimensions. It just doesn't have a direct. I don't have a direct sort of geometric meaning, but I can give you other interpretations for this integral. So here's some other interpretations. For example, or applications really. So example 1, if lambda is equal to the mass per arc length, all right, so mass per unit length along a string or something, then of course dm is lambda ds, right? So total mass along C would be the integral of C lambda ds. So I could calculate the total mass of a curve that was, in 3 dimensions or 2 dimensions. Just integrate the mass per unit length along the curve. This notion of integration does that for me. I could also have something like lambda is charge per unit length, right? Then the total charge along a wire, right, would also be the integral along the curve of lambda ds, where that lambda was, of course, the charge per unit length. I mean, these are applications of this notion of integration that are not directly geometric, they're more physical. All right? I mean, I like these basic tent pictures to give you some kind of, sort of rudimentary geometric idea about it, but ultimately it's more about adding up infinitesimal things in my view. Okay, well, let's look at an actual example with a, some things in it. This may be similar to what I had in the video yesterday, but that's probably okay. maybe it's not, I don't know. It might be worth recasting the definition. Let me just give you the definition dot notation version. Some of you might prefer this. I don't know. The integral over the curve of f ds is equal to the integral over the parameter range of f of, x of t, y of t, z of t, times the square root of x dot squared plus y dot squared plus z dot squared dt. What is the thing that, what's the double bar dr dt? What is that? What do we say that is? This is the what? Magnitude of velocity, otherwise known as speed. Very good. So the arc length integral just says you integrate the function evaluated at the parameterization times the speed times dt. That's it. By the way, the arc length integral, what happens if you put f equal to 1? What do you get? Just what? But if we just integrate ds, what should that give us? It should give us s, right? That will give us the total arc length of the curve. Don't try to make it more difficult. It's not. So example 3. Let's say f of x, y, z equal to x plus 3y plus z. And let's let the curve be line from 0, 1, 2 to 3, 4, 5. Let's calculate the integral with respect to arc length of that function over that curve. Right? So I want to calculate the integral, task. Calculate the integral over the curve of f ds. So what do I have to do to be successful at this example? What do I need to be able to do? One of those things you're supposed to be able to do at this point. Yeah, parameterize the curve. We're talking about a line from 0, 1, 2 to 3, 4, 5. So how do you do that? I'll start you out. 0, 1, 2 plus t times what? 3, 4, 5 minus 0, 1, 2. Yep. So in other words, we get r of t is equal to, what is it? It's 3t, 1 plus 3t. And what do we got? 2 plus 3t? So what's the speed? Well, what's dr dt? We got 3, 3, 3. Oh, it's kind of boring. So what's the speed here? Yeah, square root of 27. So what's my integral? Integral of f ds over the curve C. And by the way, the thing that you guys should have told me, what's the parameter domain here? That kind of matters, right? This is for 0 less than or equal to blank, less than or equal to blank. I'll put the t in the middle. There you go. You fill in the upper blank. What's our setup here? What is t range over? Why does that matter? That matters a lot here because that sets up what? The bounds of integration. So integral from 0 to 1. And then we're supposed to do what? F of 3t, comma 1 plus 3t, comma 2 plus 3t. And then the ds, well, The ds we just worked out is the square root of 27 times dt, actually. I mean, that's the speed times dt is ds. Yep.
How did you know the bounds were 0 and 1?
Because that's our construction. This is, this is the parameterization for a line that goes from, 0, 1, 2 to 3, 4, 5. So it's by our invention that the formula that goes from there to there, with this being t equals to 0 and this being t equals to 1, if I want that to be so, I write down precisely this rule here. Mm-hmm. If you had arranged to parameterize the line differently, we could have different bounds. One of the neat things is that if you chose a different parameterization for the curve, it actually does not change the value of this integration. Because when you reparameterize the curve, what ends up happening is your reparameterization of the curve, it changes both the bounds and the speed. And inversely so, in such a way that the net change is that the integral is unaltered by a different choice of parameterization. But now we're getting ahead in my lecture. That was later. So I used to do that at the start, but it occurs to me I should give you some examples first. So I'm doing that. Okay, but this is kind of a new thought process for you guys. What does this mean? F. So look, this is my x, this is my y, this is my z, right? So I actually need to plug those in. This is the integral from 0 to 1. So I'm supposed to do what? The rule is x, which is 3t, plus what? 3 times y. My y was 1 plus 3t. And then what? Plus z. My z was just 2 plus 3t. And all of that times square root of 27 dt. Starts getting a little, work myself into a corner again. How many t's do I got? I don't know. 3, 9. 3 plus 9 is what? 12. Looks like I got 15t. I see a 15t plus what? 5? Yeah. Yeah. Oh, yes. Thank you. Yeah. So you can pull that out front, right? It's constant. Okay, so we have the integral of f ds is square root of 27, which is, of course, 3 root 9 if you want. I mean, well, 3 root 3, I guess, right? Integral from 0 to, well, yeah, I'll write it down one more time. I am not making a math step here. I'm just copying blindly. 15t plus 5 dt. How do you do that kind of integral? Well, that's 15 halves plus 5, otherwise known as 25 times the square root of 27 divided by 2. Yeah. Fractions. 5 is 10 halves. 10 plus 15 is 25. All right, let's do another example. Well, let me see, can I get any more mileage out of that one? Another thing you could define, which would be interesting, and we should maybe start working on it, is the average. The average over C would be 1 over the length of C times the integral of f ds. So to get the average of a function on a curve, what you do is you calculate the integral of the function along the curve with respect to arc length and divide by the arc length. That gives you the average of the function over the curve. This is the straightforward generalization of the one you learned in Calculus 1. Do you guys remember this one? Maybe you remember this, maybe you don't, I don't know. 1 over b minus a integral from a to b of f of x dx. Remember that? That was the average of a function from a to b. If you wanted to replace the area under the curve y equals f of x, you could replace it with a rectangle of height, f average, from a to b, just the same. This would give you the constant curtain over the curve that would have the same area as the curved variable height curtain. Anyway, what's the average of, so for my example 3, what would the average be? Well, what's the length of this curve? Do we need to calculate an arc length integral to calculate the length? It's just what? Distance from where to where? Zero, 1, 2 to where? 3, 4, 5, right? Which is also the length of this vector, right? So that's the magnitude of 3, 3, 3. It looks like it's a square root of 27 again, huh? So the average here for my example 3 would be 1 over the square root of 27, right? Times, well, 25 square root of 27 divided by 2. So apparently, the average is just 25 over 2 for that function. Any questions? Right. So, example 4, let's let f of x, y, z equal to x squared plus y squared plus z. And let's calculate the integral of f over the arc length for c, the helix given by, well, I think we could use more practice rather than me just telling you the formula. For c, the circle, with radius 2 centered at, let's say, 0, 0, 8, where the circle lies in the z equals 8 plane. All right. So our first order of business really is to parameterize the curve, right? If we can't parameterize the curve, we can't calculate this integral with respect to arc length, right? I mean, this is why, actually, you thought maybe parameterizing curves was just something that I invented to be mean to you. Not the case. It's actually how we actually calculate integrals of interesting physical things. We need parameterizations of curves, of surfaces, to actually formulate these integrals. So, you know, how about this? So we want what? I'm just going to write it down. We want x equals to what? Square root of 2, right? Cosine t, yeah. Y equals to what? Square root of 2 sine t. And how about z? Yeah, z equals to 8. That will give me a circle in the z equals 8 plane with, you can check it, right? X squared plus y squared equals to what? 2. Yeah. I mean, I can draw a picture. So here's the z-axis, right? And so the intersection of the x squared plus y squared equals 2. I mean, x squared plus y squared equals to 2 is a cylinder in 3 dimensions, right? It intersects the z equals 8 plane at the circle we're interested in. Now, I just wrote a counterclockwise oriented parameterization. What do I mean counterclockwise? So if we take our thumb, point in the direction of the axis, our fingers kind of wrap around. I mean, the orientation of the circle's like this, actually, guys. It's going that way there. And it has the same sense of orientation as the usual polar angle. Okay, anyway, that said, I think this one, you know, if I start down this path, this choice of notation, then here it's nice to use the dot notation way to do it, you know? So dot notation, what's x dot? Square root, well, sorry, minus square root of 2 sine t, right? What's y dot? What's z dot? 0, right? So essentially the formula, guys, is that ds is the square root of x dot squared plus y dot squared plus z dot squared dt. I mean, you can rip the formula apart into pieces like this. And so this piece is really just going to give us what? Root 2 minus root 2 sine t squared, right, plus root 2 cosine t squared plus 0 squared dt, which is what? Yeah, it looks like the square root of the square root of 2 squared, which is also known as square root of 2, I think. Right? What's that? 19? Oh, yeah, don't forget to, I mean, but it's tiny. What's the harm? Yeah. Fair enough. I'd take off points on your test. Just take off points on my board. But OK, so after we clean up the mess here, square root of 2 times dt. Yes, sir?
So why have we chosen to denote dx over dt as just x with a dot over it?
Oh, this is this notation goes back to Newton. So there's two popular notations in calculus. Newton said x dot was the derivative of x with respect to time. Leibniz said that it was dx dt. But these are just 2 different notations for the same thing. Mostly it's because x dot's easier to write. It's not especially exciting, but it's true.
So x dot and it works with x prime too?
Yeah. Well, the thing is, dot is almost universally reserved for a time derivative. I mean, there's also x double dot, which would mean the acceleration. Or don't be a, you know. So, sorry. Stop making jerky comments. Let's see here. Oh, anyway, so let's stick a fork in it here. Integral C f ds, integral of what? One thing I neglected to say, I keep forgetting to emphasize this, is in order to set up the integral, we have to declare the range of the parameters, right? So if I'm going for the whole circle, I better go what? Yeah. So I should integrate from 0 to 2 pi of the square root of, and I need to calculate f too, right? So I'm supposed to take f of what? F of root 2 cosine t, root 2 sine t, and 8, right, times ds. Well, let me write ds, actually. It's important not to write ds here. If I put these over here, guys, once I write 0 to 2 pi, I cannot put ds over there. That is not correct. Once I've put 0 to 2 pi here, I've committed to writing a dt. Because the 0 and 2 pi are connected to the dt. They're part of the same integration process. So, like, it's not up for grabs. I got to write dt. Anyway, but what is this? See, so when I plug in, again, this is what? X, this is the y, this is the z. So I plug those into my formula, which is given for the function of x, y, z. What does that return? Yeah. So the x squared plus y squared simplifies to give me a what? A 2 plus z, but z is 8, so I get it. That whole thing is just 10. So I get 10 times the square root of 2 dt. And so that is simply 20 pi square root of 2. And there you go. Because that's a constant, so we just multiply the constant times 2 pi for such an integral. What would the average of this function be over the circle? What's the length of the circle? We have another name for this. The circumference, right? Which is what? 2 pi times the radius, which is 2. Hey, did you guys let me put the radius to be what? I sold you guys a bill of goods and you didn't stop me. Sad, 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 sad. You guys gotta think for yourself. You want people just tell you what to do? Like, government tells you 60% tax, be like, oh, okay, whatever. Not mine. I'm not in the government, not my business. 60%, fine, whatever. No, you need to think critically, like stand up for yourself and stuff. Square root of 2 is nonsense. That makes radius square root of 2. I mean, I'm going to fix the problem because, as I've told you before, I earned a PhD in math, and it gives me the right to do this. But, you know, short of that privilege and right, I'd be in trouble here. We have parameterized a circle of radius root 2. Right? We should have x squared plus y squared equals to 4 for a circle of radius 2. It troubles me that none of you were bothered by this. Or some of you were bothered by this, but are so uncaring for your peers as to not share the knowledge which you hold with others around you. This is not the Liberty Way. All right, unnecessary rant over. So the circumference of this circle of radius root 2 is 1 over 2 pi square root of 2, right? And then the integral of f over the curve ds, that's the average, right? So that's 1 over 2 pi square root of 2 times 20 pi square root of 2. So what's the average? It's equal to pi's, they be canceling, square roots of 2's, they be canceling. 10. This is, in fact, a very unsurprising result. Why? Should you even need the notion of calculus of arc length to tell me that the average of the function was 10 on this curve? I would argue you shouldn't, because if you just evaluate the function on this curve, right? In other words, if you plug in the parameterization of the circle into the function, like we did, this step right here, going from here, this right here, and you guys all told me that that simplifies to 10, right? What that says is that when we plug in a point on that circle, the value of the function is 10 at every point along that circle. In other words, this function is constant with value 10 on the whole circle. Of course, its average is 10, right? In fact, honestly, this one, you could just calculate the arc length, this integral, by just multiplying the arc length times 10. If you wanted to go around this circle 30 times and ask me what the integral with respect to arc length of this function was, it would just be 30 times the circumference times 10. All right. Any questions? All right. Let me use the projector here for a bit. There is a theoretical tidbit that I should talk about with you guys. I should I mean, I could write these things out. It would take me a long time to write them out properly. Some of you would actually write down what I'm writing, but even so, I'm not sure it's a good use of time. But it is important for us to talk about this theoretically. It's an important aspect of what we're doing. So I will take some class time to talk about this. And also, just because I want to put up the definition, the other remaining application in here, guys, is the center of mass. Well, the example I had you watch yesterday was that, right? So that's the other remaining thing, is that if we calculate 1 over mass times the integral of x dm over the curve, 1 over mass times the integral of y dm over the curve, integral of 1 over mass times the integral of z dm over the curve, that gives us the so-called center of mass. I'll come back to that in a minute, but all right. So one of the things we haven't talked much or hardly at all about in here yet is the notion of reversing the orientation on a curve. So it's very simple, really, the idea. You know, I've got a curve. It goes from here to here, right? It goes from point P to point Q. To reverse the orientation, I just want the same set of points to be covered, but in the opposite order, right? So if this is gamma, this would be the reverse of it. And so if P is gamma of A and Q is gamma of B, I want that to be the gamma reverse of A, and I want this to be the gamma reverse of B. So what's the formula? The formula to reverse the parameterization, you just take the original path, add the parameters together, and subtract time. And what that does, what this does right here, is if you plug in, what happens if we plug in t equals to A, what do you get? gamma reverse of A gives me what? It gives me gamma of B. So the initial point of the reverse curve is Q, right? And if I plug in time B, I get B minus B, which gives me A. So the final point, the terminal point, if you will, on the reversed curve is P. So P is the starting point for the curve gamma. It's the ending point for the reverse, and vice versa, right? So this is a reversal of the curve. Here's a specific example. I look at the reversal of a parameterization of a line. Not important, really, at the moment. The larger and rather unsurprising calculation here is if we have this relation that gamma of t is equal to gamma reverse of a plus b minus t. I mean, that's essentially the definition. This is a close cousin to the definition. Here I've got it written in the other way around. If I plug in t, if I put t equal to like t plus, well, I at least, goodness gracious. Suppose t is equal to tau plus a plus b for the sake of discussion. Then what's gamma reverse of tau plus a plus b equal to? A plus b minus tau, right? Well, excuse me. A plus b minus what? A plus b minus tau plus a plus b. In other words, just gamma of tau. So my point is, I still messed it up somehow. Oh, let me stop this. What I have in the notes is fine. I'm just blathering. So this is a consequence of what I have written on the board. And the point is, if you differentiate this, we find something that's geometrically completely unsurprising. The derivative, the velocity of the original curve, is minus the velocity of the reversed curve. I mean, that makes perfect sense, right? If I look at a point here, the velocity for the original curve would be like that, right? The velocity for the other curve is the same direction, but just opposite. They're anti-parallel, right? By the way, one of the dangers of the supplemental, I mean, I wouldn't penalize this on the test probably because we haven't talked about it a lot in here, and I've given you material which confused the point, but I personally like to use the language collinear. It means it could be parallel or anti-parallel. For me, parallel means, I use parallel in an oriented sense. For me, parallel means they're both going in the same direction. Anti-parallel means they're in along the same line, but opposite directions. And then collinear is either case. It could be parallel or anti-parallel. Both of those go together to be collinear in my thinking. But I think the supplemental homework I gave you uses the term parallel in place of my collinear. So, different books, and maybe that's the dominant usage. But I'm just telling you by default, when I say parallel, I mean both going in the same direction. If there's a point of confusion about that terminology in a test or quiz or something, you just ask me, all right? All right, moving along. Moving along here. So if you have a path that has range of parameters a1 to b1, and you have another path, say, that has range of parameters a2 to b2, the gamma 2 is a reparameterization of gamma 1. If you can find a change of parameters map, mapping u, which takes a1 b1 to a2 b2, which has continuous inverse, such that gamma 1 of t is equal to gamma 2 of u of t. This is like what we did with, we took remember we did the arclength, the unit speed reparameterization of the curve? That's a specific example of this idea. We traded our t for an s of t. And so we traded the original parameterization for the arclength parameterization. We could think about this idea more generally, all possible reparameterizations of a curve. And so if you think about that, the relation between the original path and a reparameterization of the path is given like this, that means that if we differentiate this, then the velocity of the original path is related to the velocity of the reparameterized path times the derivative of the reparameterization map itself, this du dt, right? So the du dt for us would have been like speed in our arc length discussion, because the u was actually s. Now there are different cases. If the du dt is always positive, then the paths progress in the same direction, so it's said to be a consistently oriented reparameterization. If you choose a reparameterization which has got du dt negative, then the paths go in opposite direction. That would be an oppositely oriented reparameterization. If you want orientation preserving, you must insist that du dt is positive. For arc length, when we take u equal to arc length, one of the things we noticed was that ds dt was speed, which is the magnitude of the velocity, which is necessarily positive. So arc length parameterization is orientation preserving. All right, so I gave you this definition today. Here's the proof that it doesn't care what parameterization you use. If I start out in the gamma 1 parameterization, integrating from a1 to b1, right? And then I trade that for a new parameterization, gamma 2, rewrite my gamma 1 in terms of gamma 2 of the reparameterization, trade my d gamma 1 for this, the du dt times the velocity in the second parameterization. Well, what happens? This pulls out, by properties of the norm, the absolute value of du dt. All right? Now, either du dt is positive or it's negative. If it's positive, then the absolute value of du dt is just straight up du dt. And that also means that u of a1 has to be equal to a2 and u of b2 has to be equal to b2, because it has to be an increasing map, so the lower bound goes to the lower bound, the upper bound goes to the upper bound in terms of the integration region. And so this reparameterization just becomes, so I drop the absolute values, the bounds stay as such. Well, they flip over to the new variable when I drop the dt and switch to u. You notice here, going from here to here, I've changed from dt integration to a du integration, corresponding to the fact that I flipped out my t bounds, which were a1, b1, for my u bounds, which were a2, b2. This is the Usubstitution theorem from Calculus 1. But what is this? This is nothing more than the integral of the arc length over the function with respect to the second parameterization. So this calculation shows that the integral with respect to arc length is independent of your choice of how you parameterize the curve. What if you oppositely oriented the curve? Right? So by the way, guys, this would be often called C. And in the language later in this course, the reverse curve is no longer a parameterization of C. It's a parameterization of what we call minus C. So typically, the reversal of oriented C is denoted minus C. Not every question I've asked you has been about oriented curves, so sometimes you can't really see the difference one way or the other. But so if we had following that general derivation, if the du dt was negative, that means that the absolute value of du dt is actually minus du dt, and also that means it's decreasing, which means the upper bound flips to the lower bound and vice versa. So when I changed from dt to du, it flips the bounds, but I also get a minus from the du dt. And so that minus flips the bounds back, and then again, voila, integral with respect to the gamma 2 parameterization. So by the way, what this little derivation shows you is that the integral over the curve of fds is equal to the integral over minus the curve of fds. In other words, the arc length integral doesn't care a lick about how you orient your curve. The arc length integral is insensitive to your choice of parameterization, whether it's counterclockwise or clockwise. The integral over the circle's the same for the arc length integral. So this is actually very different. I mean, so I made an analogy to this earlier, right? But that analogy has limitations, because certainly if we change the bounds from a to b, from b to a, right, if we reverse the bounds, it makes a sign. you know? But anyway, let me digress, not digress further there. All right. So here was the last thing I just wanted to say again in class in case some of you haven't watched the video. So if you have a curve with length L, if you have dm, ds is delta, the mass per unit length, the total mass of the curve is found by integrating delta ds. The centroid, or center of mass for the curve, is just x bar, y bar, z bar. It's 1 over the total mass integral of x times the density ds. The y coordinate of the center of mass is 1 over m integral over c y delta ds, and the z coordinate of the center of mass is 1 over m integral of z delta ds. So I actually, in that video I asked you to guys watch yesterday, I calculated it, I think, for a helix with a slightly interesting mass density. That might have been this example, I don't know. Maybe not. Now there are not a lot of problems in my current at the end of chapter problems. Problems 187, 188, and 189, which appear later in later chapters, actually give you a few examples of this section. Now, you might wonder, why on earth am I doing this right here? So my brother swears by this. He's taught Calc 3 for a few years, and he insists that covering the integral with respect to arc length here helps demystify the line integral later in this course. For me, the jury's not out yet. I think he's probably got a point. I'm not totally convinced yet, but I'm still trying to kind of follow his idea and see how it works out. So you guys are still part of an ongoing experiment on my part to cover this at this point in the course. If you look at standard textbooks, it's not here. Typically, this material is delayed way later, but it really only requires parameterized curves and functions, and it's a logical application of the calculus of curves that uses integration in an interesting, applied, and not stupid way. And I think it's a good application for parameterizations, which probably helps them be a little bit less mathemagical to you, perhaps. I mean, I think it's neat. You have a curve of variable density. What's its total mass, right? Integrate the mass density along the curve. If you had something like, well, I'll stop. Do you guys have any questions? I'd really rather not do daily quiz today. Is that all right with you guys? Let's talk about what happened in the. Well, let's not talk about what happened to me Monday night. Let's not talk about how I felt Tuesday.
How do you feel today?
Let me put it this way. For you to understand how I was feeling Tuesday, I will say it to you in the most serious way I can think. I would rather have been teaching physics lab. So for those of you who know me a little bit, that tells you something right there. Finding new ways to insult physics lab every semester, it's kind of fun.
I just had my first physics lab yesterday, and I feel your frustration.
You should feel nothing. It's easy peasy. I mean, it's a walk in the park. It's in and out, 2 hours, you're done. Woohoo! But let's see, where was I? Oh, math battle, right? So 2 things. Well, you guys, your choice. Tomorrow we have a quiz. Eventually I'll get my thought together. The quiz will be on, yes, the things like in the math battle, but also what we did today and yesterday. We being me from last year, and you possibly, hopefully. So I will ask a token question on the quiz that's the integral with respect to arc length, perhaps finding the centroid. Listen, would it be helpful to you guys to have a 3x5 card with notes?
Yes.
Yeah, I won't provide it, but you can provide one for yourself. But 3 inches by 5 inches, so we're clear. Not 3 meters by 5 meters or 3 feet by 5 feet. You can write on both sides, but only 2 sides. Okay, just to be clear. Every once in a while I have some clown who tries to write on the internal plies of the 3x5 card. I've seen it done. Single 3x5 card, he splayed it along its, got inside, if you get a thick enough one, you can cut it down make it into 2. I mean, I feel like if you do that for yourself, I should almost allow it. It's kind of impressive, but I really, on the other hand, we want to encourage you to use your time in pretty much any other way possible. I mean, I think even canoodling out in the Mont View would probably be better. I'm sorry, is that a word, canoodling? Pretty sure what I happened to come here after hours, and I noticed that the amount of PDA, like inappropriate PDA, like, God, just amazing. To be a single person around here, it's got to be horrible. Anyway, where was I? Oh, I was trying to show you something, and I think I distracted. Where were we? Where'd that test come from? I don't even remember. Was it 14? Was it? We'll know it when you see it, right? Is this it? It had 17 problems. This one's only got 15. This is not the one we're looking for. Come on, where'd you go? Looks like we're looking something circa 2015. That's where I got your test. Okay, so is there anything in particular you'd like to discuss, either from the Math Battle, aka Test 1 of 2015, or, and by the way, that's not how Math Battles typically, Professor Long contacted me as like, there's any quiz or something that I could do today, and I thought, well, giving you guys the quiz on Tuesday would have been just ridiculous, right? But Math Battle, in the format I gave you, should have been a welcome experience. It shouldn't have been bad, I hope. Yeah. Let's see here. Oh, did I not have that typo fixed on your test? What did I have there?
You probably had cosine again.
It was cosine cosh.
It was fixed?
Cosine cosh, yeah. Was it sine?
Cosine? Oh, it was cosine cosh?
Yeah.
Oh, yeah.
Oh, I get sine cosh. I had sine cosh.
I think I fixed it. I usually try to fix these things afterwards. Let me, just a second here, I'll tell you. I know which one I gave to. I was careful to give him not the original, quote unquote, but the fixed one. Yeah, so here's the one you guys did. Yeah, it's fine. So the idea here, guys, is that if we square this and that, what happens? We get the 3 and the 2, no! So I got to think something harder than that, right? 3 and the 2 are cramping my style. So my knee-jerk reaction was just to square x and square y, add them together and see if I could get something nice. But what got in the way of that? The coefficients, right? But those are easy enough to remove. Just divide, right? So if we look at x over 3, what do we got? Oh, 2. Grief. It's not a good sign. X over 2 is, what was it, cosine theta? Cosh beta. And y over 3? Sine theta, cosh beta. And what was my z? So it's all about, almost all these problems boil down to creative uses of cosine squared plus sine squared being 1 and cosh squared minus sin squared being 1. Hold those two thoughts near and dear to yourself. You could solve almost any one of these problems if you understand what you're trying to do. What are you trying to do here? What's the big picture of what we're trying to do here? Find the Cartesian equation. What's that mean? The Cartesian equation has only x, y, and z, or some subset of those. So we have to eliminate theta and beta.